I'm going to draw some graphs for some continuous functions, and we're going to analyze that end behavior first. So I'm actually going to draw 4. I'm just going to put one on top of the other. I have 2 columns here. So to discuss end behavior, it is really all about the arrows. So we are looking for how each of these graphs behave at the arrows after it's off the picture. So the first graph that I'm going to draw is going to be what is considered a positive graph, and I'll show you why. I'm going to draw something that kind of looks like the letter W. That is for sure a function. If I trace it, that is not a vertical line. It's increasing pretty steep, but that is not a vertical line. When I trace this, none of my x values repeat, and I know it's continuous because I would not have to lift up my pencil to draw this shape as I move from left to right on the coordinate grid. Let me show you another positive function. That is also considered a positive function. Now let me draw a couple of negatives, and maybe you can kind of start seeing why I'm calling these graphs that I'm about to draw negative. All right, so those are for sure negative functions down here. These are 100% positive functions up here. And the reason why I know that, it is so simple. I just know because of the arrow on the right side. Always the arrow on the right side. If you have an arrow that is up on the right, that function is positive. There is a positive leading coefficient there. Same for this. They are both positive for sure because I have an arrow up on the right side of my picture. Now, if I have arrow down on the right, still analyzing on the right, then I know the function is starting with a negative. So it has a negative leading coefficient. One more thing before we start talking about end behavior. So not only can functions be positive or negative, they could also be even or odd. And I know we talked about that earlier when we were discussing symmetry. Now again, I know for sure that we are going to have an even based on the arrows. I know we're going to have an odd based on the arrows. So if you notice, both of my arrows are pointing in the same direction for this first graph. My arrows here are pointing in opposite directions. So if you have arrows in opposite directions, then that is considered an odd function. Now, I'm not saying it is necessarily symmetric around the origin. I just know that this function is odd because the arrows are in opposite directions. One more is going to be an even function. An even function has arrows pointing in the same direction. Anytime I see 2 arrows pointing down or 2 arrows pointing up, that is an even function. Okay, so let's start hopping into in behavior. So remember, for end behavior, it's all about the arrows, and we scan it like a graph from left to right. So the first thing I see is an arrow. Arrow means infinity, and this is the negative infinity part of the x-axis. So as my x values continue to go up, they're also getting lower and lower and lower. So as my x approaches negative infinity, then this function is going higher and higher and higher. So the lower my outputs, the lower my inputs, the higher my outputs. So that's approaching positive infinity on the left arrow. As my inputs get bigger over here, oops, that is an infinity symbol. So do my outputs. So this is also approaching positive infinity. And remember, that is an infinity symbol. I'm going to make that cleaner on the PDF that I'm loading. That's an infinity symbol. All right, so left arrow's going up. Positive outputs, positive inputs. What you need to notice here is this function's outputs both are going up, up, up. Same end behavior. So if the arrows are pointing the same, it's an even function. Now we get to add something else to this. They are going to have the same end behavior. All right, let's analyze the opposite. Over here, this is a negative infinity arrow, so as x approaches negative infinity, I know it's negative infinity because it's to the left of the origin. What's happening to my outputs? Well, as my x values get lower and lower this way, my outputs are getting lower and lower down. So as x approaches negative infinity, so does f of x. Let's look at the right side. Right arrow right here. So as x approaches positive infinity, so do the outputs. So if you notice here, these do not match. And if it's an odd function, they never will. So now we get to add more info about this odd function. So opposite end behavior, opposite arrows are always going to give you opposite end behavior. And that's going to be the same for negative functions right here. Look, as x approaches negative infinity, here's my left side arrow, f of x is approaching negative infinity. However, on the right side, if my outputs get larger over here, if my inputs get larger over here, my outputs are still getting smaller. See how they have this same end behavior for the outputs. No matter if they're getting larger or smaller as inputs, the outputs are always getting smaller. All right, over here, as x approaches negative infinity, look, this time it's flipped. As my inputs get smaller and smaller and smaller, my outputs are getting bigger. So this is approaching positive infinity. Over there on the right side arrow, remember the right side arrow is positive infinity. Let's take a look at what's happening to those outputs. It's going down. So as my inputs get larger, my outputs are getting smaller. Notice these end behaviors for the outputs are opposite. And that is going to be a brief introduction into end behavior.